Hello dear friends, welcome to this lecture of vector spaces. In this lecture we will start the study of inner product spaces, and also we shall define the inner product space and we shall study some examples of inner product spaces. I have written the definition here. It is a vector space associated with which an inner product is associated, and that vector space is called inner product space. The definition is the vector space V over F. F is a field, is said to be an inner product space if there is defined for any two vectors u v belongs to V, an element. This element we call it as this is a notation for inner product of u and v in F. This is the element in F. That means actually the inner product is a function from V cross V, or it is a function from the vector space is V cross V to F, that the product's value is in the field. F is field, V is a vector space over the field F, and we are defining the inner product in the vector space V. U and V are elements of V, then their product is denoted by this parenthesis order pair u and v, and we read it as inner product of u and v, and its value is in F, that is in field, such that it satisfies these three properties. The first is inner product of u and v is equal to conjugate. This bar means conjugate of inner product of v and u. That is the first property. And second property is inner product of u with itself is greater than or equal to 0, and inner product of u with itself is equal to 0 if and only if u is 0. So, this is known as non-negativity property. This is the conjugate symmetry property, and the third is, this property is also known as linearity property. Here the inner product of alpha u plus beta v, u and v are vectors, we consider another w is also a vector. These are three vectors u, v, w in V, and alpha, beta are scalars that are in field, and then the inner product of this combination of u and v, alpha u plus beta v and w is equal to alpha into inner product of u and w plus beta into inner product of v and w. So, these are the three properties which are necessary to define an inner product. If these three are satisfied, then we say this is inner product, and the vector space becomes inner product space. Now, we have written some remarks here. In this definition, the field F is either of field of real numbers or field of complex numbers. If F is a field of real numbers, then the inner product space is called as Euclidean space, and if F is a field of complex numbers, then it is known as unitary space. Second remark is this notation. Bar notation denotes conjugate of a complex number, we know. So, conjugate of u, inner product of u and v and u, inner product of v and u, its conjugate of inner product of v and u, and so it is a conjugate of this product. And for example, what is meaning of conjugate? For revision I have written here, z is complex number x plus I into y, I is equal to root of minus 1, and then what is the conjugate of z is x minus iy. That means we change the sign of this imaginary part, then we get its conjugate. And some properties of conjugate are double conjugate of a complex number is the same. Double conjugate of z is equal to z, and z into z bar or z into conjugate of z is denoted by mod z, means modulus of z whole square of modulus of z, and that is x square plus y square. You can easily verify what is the product of this x plus iy and x minus iy, that is x square minus I square y square, but I square is minus 1, therefore it becomes x square plus y square, and these x and y are real numbers, their squares are positive, and therefore positive or 0 or non-negative, and therefore this quantity is always greater than or equal to 0. That means, remember, mod z square is greater than or equal to 0. And some other properties are conjugate of z1 plus z2. z1 and z2 are two complex numbers, then the conjugate of their sum is equal to sum of their conjugates, z1 complement plus conjugate plus conjugate of z2. Similarly, the conjugate of the product of z1 and z2 is equal to product of their conjugates. And now we will write third remark as using the properties 1 and 3 in the definition. So what we can write is about this linearity property in linearity in second argument. This is linear in the first argument. Inner product of u and alpha v plus beta w. We first apply the first property. The inner product of u and v is equal to conjugate of the, if you interchange the vectors v and u. So therefore we will interchange the vectors and take its conjugate. So this will be the first vector will be alpha v plus beta w, and second vector will be u and its conjugate by property 1. This is by 1. Interchange the vectors and take the conjugate, that is the first property. And now see, for this we should use now the second property, third property. Here the third property is direct. Inner product of alpha u plus beta v and w is this much, and therefore we can write this is equal to alpha into inner product of u and w. But see, what we have written here is alpha u plus alpha v. It is alpha v plus beta w, and therefore this will be alpha v and inner product of v and u. So this is inner product of v and u plus beta into inner product of w and u and its conjugate. This is conjugate of this whole by 3. This is by third property. See, alpha inner product of u and w, alpha is scalar, and plus beta inner product of v and w. Same result we have used here. The vectors are different here, and now this will be equal to, see, we use these properties of conjugates. Now we can separate the conjugate, we can separate here also, and that will be alpha bar conjugate of inner product of v and u plus conjugate of beta conjugate of inner product of w and u. And now we again use the first property here, and that will be alpha bar, and see, conjugate of inner product of v and u is inner product of u and v. So this will be inner product of u and v plus beta bar, and this is inner product of u and w. And now you can see, if you take alpha, if this combination is in the second vector, then these alpha and beta becomes conjugate. If you write outside here or in this right side, alpha becomes alpha bar or conjugate of alpha, inner product of u and v plus conjugate of beta, inner product of u and w. So this is the result that we shall remember, and this is the basic result or in the definition, which is the property 3 known as linearity property. So these are the 3 conditions for inner product space, and if a product defines all these 3 properties, then the product is known as inner product, and the vector space becomes inner product space. Now we shall consider some examples of inner product space. See examples. First example we shall consider as, in Fn the vector space Fn. F is field, and it is a vector space over field of n dimensional vector space Let, and we know what are the elements of this vector space. It has n tuple. Let u vector in this field will be having n components, alpha 1 up to alpha n. That is one vector we have considered in Fn, and second vector we shall consider as v is equal to beta 1, first component beta 1, beta 2 up to beta n, second vector. We have this, and now we define the inner product between u and v as define inner product of u and v as alpha 1 conjugate of beta 1 plus etc. alpha 2 conjugate of beta 2 and so on up to alpha n conjugate of beta n. See how the product is defined. Inner product is defined between u and v is alpha 1 conjugate of beta 1. The second component will be alpha 2 conjugate of beta 2 plus so on, and last term is plus alpha n conjugate of beta n. So that is the inner product is defined. Now see, inner product is similar to a dot product or scalar product of vectors, and it satisfies this. Actually this inner product satisfies the properties of dot product. We know the dot product is commutative, and if this is real, if a number is real, its conjugate is itself, and therefore if this inner product is real, then inner product of u and v is same as inner product of v and u. And second condition will be the inner product of a vector with dot product of a vector with itself is greater than or equal to 0, or if it is 0 then the vector is 0, and this is the linearity property. Now we shall have to verify all these three properties for this product. Define this, show that this defines an inner product. Inner product on this vector space Fn. We have seen this is a vector space earlier, and now we have defined inner product by this definition, taking two vectors. Two vectors are taken and its product is defined in this way. There are the product may be defined in different ways, and this is the definition we have given or we have considered, and we will show that this defines inner product. This definition defines inner product, means this product satisfies all these three properties. Now the solution for this is, first we shall verify the properties, these properties. So we have first property, that is inner product of u and v is equal to the conjugate of inner product of v and u, that we have to consider or show. See, for first we have inner product of v and u. Now what will be inner product of v and u? So we have to interchange v and u. First consider v, then consider u. That means in place of alpha, betas will be there, and in place of beta, alpha will be there. That means alpha beta are interchanged, and therefore this inner product will be beta 1 alpha 1 bar plus beta 2 alpha 2 bar, etc. And I shall write last term, that is beta n alpha n bar. And now we will show this first property from right side to left side. That means take its conjugate and show it is equal to the left side. Now taking conjugate of this, therefore the conjugate of the inner product of v and u is equal to conjugate on the right side also, beta 1 alpha 1 bar plus beta n conjugate of alpha n and whole conjugate of the whole expression. So this is by the property of conjugate of complex numbers. We can take the conjugate of each separately, and this will be beta 1 alpha 1 conjugate of alpha 1 its conjugate plus so on conjugate of beta n conjugate alpha n. And now we know that is conjugate of Z1 Z2 is conjugate of Z1 into conjugate of Z2, and that is equal to beta 1 conjugate of beta 1 double conjugate of alpha 1 and plus so on. This is conjugate of beta n double conjugate of alpha n, and we know double conjugate of a complex number is itself, and that is this will be beta 1 conjugate of beta 1 alpha 1 z double conjugate of z is z, and therefore this is equal to conjugate of beta 1 alpha 1 plus so on up to conjugate of beta n alpha n, and this is exactly the given definition. See, alpha 1 conjugate of beta 1. So, this product is commutative, and therefore, this is exactly same as inner product of u and v, and thus we can write this as, I shall write here itself, this is conjugate of u and v, inner product of u and v, v and u is equal to, this is alpha 1 beta 1 conjugate plus alpha n conjugate of beta n, which is same as inner product of u and v, and thus the first property is verified. So, we have verified the first property. Now, the second. So, the second property is this one, inner product of u and u is greater than or equal to 0. So, we have for the second property, inner product of u and u is equal to, now see the definition again, inner product of u and v is this having this expression. So, v is replaced by u here in this product, means betas will be replaced by alpha only, because the same vector we have to consider with the product, and thus this will be alpha 1 conjugate of alpha 1 and so on alpha n conjugate of alpha n, and we know that z into conjugate of z is z mod z square, and therefore, this will be mod alpha 1 square plus so on mod alpha n square, since z bar is mod z square. This is the reason for this, and see, each is a square, and therefore, each quantity is non-negative, and therefore, this expression is greater than or equal to 0, it cannot be negative, and thus this is greater than or equal to 0, and this is the first part in the second property. Now, what is the remaining? Inner product of u and u is 0 if and only if u is equal to 0. I shall write it here. Next, inner product of u and u is equal to 0, and that this is 0 implies and implied by. So, double implication, if and only if we should write like this. So, what is the inner product of u and u? Here it is. This means mod alpha 1 square plus so on up to mod alpha n square. This is equal to 0. This is equal to 0, and when this will be equal to 0, each is having square form, that means each is non-negative, and the sum of non-negative numbers is 0, means each must be necessarily 0. Each term must be necessarily 0, then and only then it will be 0. So, this implies alpha I is equal to 0, mod alpha I or each alpha I is equal to 0. This implies alpha I square is equal to 0 for each I is equal to 1 to up to n, and this implies alpha 1, alpha 2 etc. are all 0. This implies alpha 1 is equal to alpha 2 is equal to alpha n is equal to 0, and each component is 0, means this vector is 0, u is 0, and thus this proves the second part of the second property. The inner product of u and u is 0 implies u is equal to 0. Now what is the remaining is the third property. Now we prove the third property here. See, for the third property, which is the linearity property, we have to take three vectors u, v, w belongs to v. Now u and v are given here. Let w is equal to third vector, w is equal to having components gamma 1, alpha, beta are used for u and v, and w will express in terms of gammas, gamma 1 up to gamma n. This is w, and let alpha, beta belongs to f, scalar. Third vector we have considered. Earlier vectors we will take as it is, u and v. Now we want to show this or we have to evaluate this product, and for that purpose we first obtain what is alpha u plus beta v. Then now what is alpha u plus beta v? This is equal to alpha, what is u? U is here having components alpha 1 up to alpha n, and plus beta, what is v? V is having components beta 1 up to beta n, and thus this can be written as this is equal to, by the definition in the vector spaces, this multiplication is written as we have to multiply by alpha to each component, and that becomes alpha alpha 1 etc. alpha alpha n. Each component is multiplied by alpha, and for the similarly for the second, each component is multiplied by beta, so it is beta beta 1 and so on, beta beta n. And again this is this now this is the scalar multiplication we have. Now addition of these two vectors is the component wise addition, and that will be first component will be alpha alpha 1 plus beta beta 1. So that is the first component, alpha alpha 1 plus beta beta 1, and so on. The last component will be alpha alpha n plus beta beta n. So this is the last component. So this is the expression for alpha u plus beta v. So first we have obtained this vector. Now we will take its inner product with w. So then inner product of alpha u plus beta v with w is equal to, now we have to observe the component of w, and first this component alpha alpha 1 plus beta beta 1 etc., that is this vector, and then w, and use this definition. Inner product of these two vectors is alpha 1, the first component of this vector, into conjugate of the first component of the second vector. So therefore this will be alpha alpha 1 plus beta beta 1, this as it is, into conjugate of this first component, that is gamma 1. So multiplied by conjugate of gamma 1 plus so on, and what will be the last? Last is see like this, alpha n, the last component of the first vector, that this here is alpha alpha n plus alpha alpha n plus beta beta n, multiplied by the component, last component of the second vector, here it is gamma n, conjugate of gamma n. So this is the inner product of these two vectors. Now we shall have to show this has the form alpha into inner product of etc. So for that purpose, what we can do is we have to multiply this by gamma conjugate of gamma 1 etc., and that can be written as alpha. We shall separate the parts. having alpha and beta. So this will be alpha 1 into conjugate of gamma 1. So that is the first vector can be written as alpha 1 conjugate of gamma 1. Then the second vector will be, and so on. That is the first vector, plus the last will be alpha n conjugate of gamma n. So this alpha parts we have separated. Now in the second part we will write beta. So beta 1 conjugate of gamma 1, and so on, beta n conjugate of gamma n. So this we have expressed. Now further this can be written as, see, I shall write here, this is equal to, from the first vector alpha is common, so we write alpha outside, and then this becomes alpha into bracket alpha 1 gamma 1 complement of gamma 1 comma, so on, alpha n complement of gamma n, conjugate of gamma n, and plus from the second vector we shall take beta common, and in bracket what remains is beta 1 conjugate of gamma 1 plus so on, comma, so on, and then beta is taken common, so it is beta n conjugate of gamma n. And you see what is this product? First it is alpha, this is inner product of alpha 1 means this vector u, and gamma 1 etc. means vector w. So this is inner product of alpha and w. We have denoted w as gamma 1 up to gamma n, and therefore this is inner product of alpha, that not alpha but u. This is inner product of u and w. And what about this second plus? This is inner product of, see, beta means betas are component of v, so this is inner product of v and w, and thus you see this is the right side we have obtained, and this shows that the third property is also satisfied. So thus all the three properties of the inner product are satisfied, and hence this inner product, this product defines inner product, and hence is an inner product or defines an inner product, an inner product on the vector space Fn. So this is our first example of inner product space. One more example we shall consider is, that is a second example I shall write. As in second example, we shall consider the vector space F2 in place of Fn. We shall consider F2, and that means two dimensional, and that case it will be F2, and we will have, u will have two components only in place of n components. U will be alpha 1 alpha 2, and v will be having beta 1 beta 2. And we define this inner product of u and v like this. It is 2 alpha 1 beta 1 conjugate of beta 1 plus alpha 1 conjugate of beta 2 plus alpha 2 conjugate of beta 1 plus alpha 2 conjugate of beta 2. We define the inner product like this and show that this defines an inner product on F2, and now we will prove it. We shall show this as inner product. This is an inner product, satisfies the three properties. We shall verify the properties. First property. First is the inner product of u and v is conjugate of inner product of v and u. Now for that purpose we first write inner product of v and u. So by this definition we have inner product of v and u. Now how to write the inner product of v and u? These are interchanged, the vectors are interchanged, and therefore alpha and beta will be interchanged, and that means this is 2 beta 1 conjugate of alpha 1 plus beta 1 conjugate of alpha 2. Beta, in place of alpha we write beta, in place of beta we write alpha, and plus this is beta 2 conjugate of alpha 1 plus beta 2 conjugate of alpha 2. So that is the inner product of v and u, and therefore now what will be the conjugate of this? We shall take the conjugate of this. That means we are proving the first property in right side to left side. We have formed the inner product of v and u. Now we are taking its conjugate and we will show it is equal to the inner product of u and v. So take the conjugate of the whole expression, that is conjugate of this right side. Conjugate of this, and by the properties of conjugate of complex number we can take the conjugate separately, and then we can write the conjugate of this product also separate. And first we can write conjugate of 2 is 2, because 2 is real number. For real number its conjugate is the same, and this will be conjugate of beta 1, or I shall write like this, conjugate of this part plus beta 1 conjugate of alpha 2, conjugate of that, plus conjugate of beta 2 conjugate alpha 1. And next, as earlier, see here actually we have used, since conjugate of z1 plus z2 is equal to conjugate of z1 plus conjugate of z2, and further that can be written as, so this is equal to 2 conjugate of beta 1 alpha 1, double conjugate of alpha 1 is alpha 1, plus that is conjugate of beta 1, and double conjugate of alpha 2 will be alpha 2, plus next is conjugate of beta 2, double conjugate of alpha 1, see here double conjugate of alpha 1 is alpha 1, and plus beta 2, and then double conjugate of alpha 2 is alpha 2. First is conjugate of beta 2, since double conjugate of z is equal to z, and again this can be written in this form. See, it is exactly the same, 2 alpha 1 conjugate beta 1 plus alpha 2 conjugate of beta 1, next is alpha 2 conjugate of beta 1, yes, that is this term, and plus alpha 1 conjugate of beta 2 plus alpha 2 conjugate of beta 2. See, this is exactly the same. So as inner product of u and v. So we have started with this and we have obtained this, hence the first property is verified, hence property 1. Now we shall go to second property, that is inner product of u and u is greater than or equal to 0. For this, second, we have inner product of u and u. By this, you see, v is replaced by u means beta will be replaced by alpha, and that is 2 alpha 1 conjugate alpha 1. In place of beta we have to write alpha 1, then this is conjugate alpha 2 plus alpha 2 conjugate alpha 1 plus alpha 2 conjugate alpha 2, and this is now we know what is alpha 1 conjugate alpha 1, that is mod alpha 1 square, and therefore this is, but I shall write this as alpha 1 conjugate alpha 1 plus alpha 1 conjugate alpha 1, double term I have written separately, and plus alpha 1 conjugate alpha 2 plus alpha 2 etc., but that remaining term I shall write here, plus alpha 2 conjugate alpha 1 plus alpha 2 conjugate alpha 2, and now the first term I shall write this as mod alpha 1 square, z bar is mod z square, and plus from the remaining terms I shall take alpha 1 common. So what remains in bracket is conjugate alpha 1 plus conjugate alpha 2, and from the last two terms we take alpha 2 common, and that will be alpha 2 common in bracket alpha 1 conjugate alpha 1 conjugate alpha 2, or this is again mod alpha 1 square plus, and here we shall take this common, then in bracket it remains alpha 1 plus alpha 2 and another bracket alpha 1 plus alpha 2 conjugate of this, and further this can be written as mod alpha 1 square plus, the second is also in this form alpha 1 plus alpha 2, alpha 1 plus alpha 2 conjugate of alpha 1 plus conjugate of alpha 2 means conjugate of alpha 1 plus alpha 2, and that is equal to conjugate alpha, this is mod alpha 1 square plus, and again this is z into conjugate z means it is mod alpha 1 plus alpha 2 whole square, since z conjugate z is mod z square, and you see both are squares means both are non-negative, and therefore this is greater than or equal to 0, this is also greater than or equal to 0 means this is greater than or equal to 0, since mod alpha 1 square is greater than or equal to 0 and mod alpha 1 plus alpha 2 square is also greater than or equal to 0, and thus what is the left side was the inner product of u and u is greater than or equal to 0. So this proves the first part of the second property. Now what about the second part? Next, see, this is 0, second properties part. Next, inner product of u and u is 0, and that implies and implied by. So we have obtained the expression for the inner product of u and u, that is here mod alpha 1 square plus mod alpha 1 plus alpha 2 square is equal to 0, and when this will be equal to 0 if each alpha 1 is 0 and alpha 2 is also 0. So this is non-negative quantity, and therefore this must be 0 and this second must be 0, then and only then its sum is 0. This implies mod alpha 1 square is equal to 0 and mod alpha 1 plus mod alpha 2 square is 0, and this implies alpha 1 is 0 and alpha 2 is 0, and this means alpha 1 alpha 2 are 0 means u is equal to 0. So because u is alpha 1 component, alpha, there are two components alpha 1 and alpha 2, and thus u is 0. So thus we have proved the second property. Now what remains is the third property. So I shall write third property here. What is the third property? Is the linearity property. Now for that we shall consider w, as in the earlier case we shall consider w as gamma 1 comma gamma 2. So gamma 1 gamma 2 having two components as w, and therefore we have further, and let alpha beta belongs to F field. We have alpha, this combination first we shall obtain, alpha u plus beta v, and is equal to alpha, what is u is alpha 1 alpha 2, and what is v is beta 1 beta 2, and this is equal to alpha alpha 1 alpha alpha 2 plus beta beta 1 beta beta 2. So this is again we have to add the component wise. We have multiplied here, scalar multiplication. Now the addition of the components, first component plus first component of the second vector, alpha alpha 1 plus beta beta 1 comma alpha alpha 2 plus beta beta 2. So this is the expression for alpha u plus beta v. Now we have to take the product of this with inner product of this with w. And therefore, so now the inner product of alpha u alpha u plus beta v with w is equal to, so this will be equal to, now you see this is the first vector and w is here the second vector. So by this definition we have to write it. So 2 into first component of the first vector, 2 alpha 1, alpha 1 is the first component of the first vector, the first vector is now here alpha u plus beta v. So that is 2 alpha 1 means alpha alpha 1 first component plus beta beta 1 into conjugate of the second vector, that is second vector is conjugate of the first component of second vector, that is gamma 1, conjugate of gamma 1 plus alpha 1 is again this first component alpha alpha 1 plus beta beta 1 into conjugate of the second component, that is gamma 2. The definition is important, and according to the definition we have to write the inner product, and plus this is the second term we have written. Now plus alpha 2, alpha 2 means the second component of the first vector, that is this is the second component, alpha alpha 2 plus beta beta 2 into conjugate of beta 1, conjugate of the first component, that is gamma 1, conjugate of gamma 1 plus, and the next is again alpha 2 means this vector same, alpha alpha 2 plus second component of first vector beta beta 2 and conjugate of the second component, that is gamma 2. So this we should have to separate alpha and beta, and for that purpose we can write this as this is equal to, now we can observe here these are the components we have written, and we will now consider alpha common. So if I write alpha common, so what remains in bracket? You see 2 alpha 1 into conjugate of gamma 1, 2 alpha 1 conjugate of gamma 1 first, and then here alpha is taken common, alpha 1 plus alpha 1 conjugate of gamma 2, and again alpha we have to consider as common, and alpha 2 conjugate of gamma 1 plus here alpha 2 conjugate of gamma 2 will remain in bracket. Taking alpha common from these 4 terms, we have written remaining in bracket. Now take beta common, and taking beta common in second terms. So what remains in bracket is 2 beta 1 conjugate of gamma 1, 2 beta 1 conjugate of gamma 1 plus here beta is common, beta 1 conjugate of gamma 2 plus here beta is taken common, beta 2 conjugate of gamma 1 and plus beta 2 conjugate of gamma 2. Now this is we see is equal to alpha into. So this expression, you see the definition here. In place of alpha, it is the same. In place of beta, there is gamma. 2 alpha 1, gamma, conjugate gamma 1, alpha 1, conjugate gamma 2, etc. And therefore, this is inner product of u and w. So what is w we have written is gamma 1, gamma 2. So in place of beta, it is w, means this is inner product of u and w. So this is inner product of u and w plus beta. And what about this second? This will be inner product of beta are the components of v and gamma are components of w. So therefore this is inner product of v and w. The second bracket is inner product of, or this bracket is inner product of gamma, inner product of v and w. And this is what we wanted to prove. Alpha into inner product of u and w plus beta into inner product of v and w. The left side is this one, and hence the third property is satisfied. Thus, all the properties are satisfied. All the three properties of an inner product are satisfied, and therefore this is inner product. This defines inner product on F2. So thus we have seen two examples of inner product. We have defined inner product, and what we have to remember is these three properties, and with the help of these three properties, verification of these three properties proves that the defined product is inner product and the space becomes inner product space. The remaining part we will continue in our next lecture. Thank you for watching the lecture.